In this video, we're going to look at an alternative method for finding volumes of solid objects that are typically, again, solid objects created by the rotation of a curve around some axis. So in the last section, the volumes we looked at were built up they were built with washers or disks. In this case, we're going to look at building a volume with cylindrical shells. And so I want to take just a quick look at both of these so we can kind of compare and contrast. So when we were dealing with washers, the idea is the shape of our washer is it was a big flat disc with potentially like a hole cut out in the middle. And if we kind of try to draw this semi-three-dimensionally, this is what we looked at. We had some sort of thickness. I'll just call it delta H. It was sometimes delta X, sometimes delta Y, depending on how we oriented the washers. And then we had some sort of radius. And so that radius was basically measured from the center out, this distance, and we could call it some sort of change in R. And in fact, I drew that incorrectly. Let me measure that up. I really want to think about it as, oops, the distance here. This is the distance from the inside hole to the outer edge of our washer. And this was some sort of, you could think of it as like a delta R if you want, a change in radius from the inside to the outside. So this was our disc or washer. When we're dealing with cylindrical shells, we're going to have a similar shape, but it's going to be more like this. So here is my cylinder. Try to draw this as carefully as I can without screwing it up too much. And we're going to have just sort of a thin shell for this thing. So if you want to think about it on the inside of this, what you can imagine is that these interior walls would go down, and we kind of just basically have like an empty can almost. And they go down to the bottom of this thing, where that interior shell continues. So hopefully that gives you some sense of the shape that I'm talking about. And in this case, we have something similar here. In this case, here is our delta H, sort of our height, and now our, what we call delta R, is really, really tiny. So our delta R, make a little more room for that. Our delta R is tiny in this case. It's sort of the wall thickness, if you want to think of it, of this tin can that's hollow at the top and the bottom. And this is the type of object we're going to use to build our solids in this case. So in the first case, in the washer, delta R was typically large. There was a significant radius with a really tiny, thin little thickness for our delta H. And here we're swapping what's large and what's small. Now it has a substantial height, but the thickness is very, very, very tiny. So it's actually kind of the same shape, just we're switching what our small parameter is in this case. And as before, we can use these shells to build, so to speak, our solid objects that we're trying to find the volume of. And so, for example, if I've got some sort of shape, I don't know, something vaguely egg-like here. So imagine that's our shape. I can build that by doing a bunch of, I do the kind of the same thing I did before. Let me see if I can kind of copy the general shape of this thing in red. Should be a little smoother, draw it nice and wobbly. But let me build this shape up with actual the type of shells that I'm thinking of. So basically, we would approximate this with a big outer shell. It goes like this. It would have a shell inside of it. You can almost think of it as almost like a wedding cake type of shape here, where we're stacking these successively smaller and smaller and smaller little cylinders, one wrapped around the other, wrapped around the other. Oops. Oh, come on now. I'll say that's good enough. You kind of get the idea, hopefully. And you can think of it as basically us, almost looks like a croissant here, and that's essentially what it is, the same way that we're building it. We're building sort of an inner one, and we're wrapping another piece around that, and then wrapping another piece around that, and wrapping another piece around that, until we fill up and approximate the original shape that we're trying to find the volume of. So this is going to be our approach. This is how we're going to build our objects. But before I can do that, I need to figure out what the volume of one of these shells is. So what is the volume of one of these shells? And so what we're going to do is we're going to take one of these shells, imagine this is what we're dealing with, and again, just so you can imagine the inside. So here's our hollowed out shell, and what we're going to do is basically snip it along here. So we're going to take little scissors, and we're going to cut it that way. Again, this little piece here is our delta R. This is what we called our H. And I'm going to think of this distance from the center out to the edge here. That distance is going to be what I'll call R, the actual radius of this cylinder that we're looking at. And if we cut along here and flatten it, we'll wind up with basically, I mean, you could do this with like a paper towel roll. That's essentially what we're doing. We're cutting up along the length of the towel, and then we're going to fold it flat. And what we'd wind up with is something that looks like this. So we'd flatten it, and we'd wind up with basically a big flat rectangle. And if I can translate some of these dimensions that we drew over here to this picture, the thickness of this thing is still our delta R. This dimension is still our delta H. And this length, the long length along this thing, is going to be related to this radius R that we've got here. This radius means that if I want to see how long this edge is once we fold it flat, it's the circumference of the circle that makes up the base of the cylinder. And the circumference, hopefully you'll recall, is 2 pi r. And so that's our formula, or our dimensions of this flattened sheet. And so what is the volume of this flattened sheet? Hopefully it's clear. The volume is going to be that V is approximately, notice I'm kind of fudging it a little bit because this R here, I drew it as going to the inner radius of our shell, but I could have drawn it going to the outer radius or somewhere in between. We're kind of fudging it, but it's approximately the dimensions that we've got here of this rectangular prism all just multiplied together. So 2 pi r delta H. And so that's what we're looking at here. if you look back at the picture of our croissant, egg, whatever you want to call it, both the radius of each shell and the height of each shell depends on the position. So basically what I'm suggesting is both this R and this delta H, they're going to depend on which particular shell we're looking at. This delta R we're going to keep the same. We're going to build our shape with consistent thickness for the thickness of each shell, but these other two dimensions can change. So the value of R and delta H both depend on the position that we're looking at. So both of those are going to ultimately be functions. So let's look at an example and see how we might put something like this together. So here we go. Let me zoom in back in a little bit here, a little too much. Okay. So this yields the following formulas. One way we can find the volume, so I'm going to skip all the summing up, the approximate things, and jump straight to the integrals in the interest of time here. But I'm basically just going to integrate a bunch of these volumes, add them all up. So we're going to integrate from some starting point, from some starting point to some ending point. And we're going to integrate, I'll pull the 2 pi out because it's a constant. And inside we'll have the R and the delta H. And in fact, the book, just let me make it totally clear. I use delta H, but really we can get away with just H. It doesn't need to be a tiny thing. In this case, the H was delta H I used in this original drawing of the washer because it was tiny. But really in this picture, it's large. So I'm going to come back and edit all of these, at least on this later one. Oh, I called it H over here, so let me call it H over here as well. Just H instead of delta H. And this will make it just clean things up, but the same idea still holds. Oh, come on now. So, seriously? Okay. Let me just start over again here. Here's the formula. This is the one that should look similar to what you will see if you read the book. So I'm going to pull the 2 pi out. We're going to integrate from some starting point to some stopping point. And we have basically some R of x and some H of x dx. And I'll draw the picture that goes with this. And if you think about it, this R of x, we'll look at that in just a minute and I'll modify this. Or another possibility is we would have v equals 2 pi times the integral from c to d. And again, the difference here is whether we're the direction that we're slicing, vertically or horizontally. So the integral from c to d of r of y, h of y, dy. And let me draw the pictures that go with each of these so that we can see how we can simplify. In fact, let me leave a little bit of space underneath it so I can modify directly below it. So here are my axes in this case, and imagine the shape I'm dealing with is some shape that looks like this. It's going to go between A and B on the x-axis. Here's the y-axis. So here are the boundaries that we're looking between the A and B direction. And maybe I have a lower bound here, and maybe the upper bound is curved and does something like this. And so this is ultimately the region that we've got, that we're interested in, and we are rotating it about the y-axis. So it would make sort of a donut shape ultimately, but the donut would be kind of laying flat on the table, if you want to think of it like that. If we do it like this, then basically, to make our cylindrical shells, we must be pulling rectangles that look like this. This must be the shape of the rectangles that we're using. And we're rotating them around so that this thing would, I'm going to draw it temporarily here in blue, it would get rotated around behind and then all the way back to where it started. And we'd wind up with a shape that looks exactly like the ones that I drew earlier. This is our cylindrical shell, so to speak. Right? That would be the shape, and we'd be doing that over and over and over with the successive rectangles next to each other. So let me erase all the blue stuff just to unclutter this a bit. Almost there. Perfect. Okay. So in this case, notice the small dimension of our rectangle is indeed in the x direction. So we get a tiny little bit of dx. The height of this thing is going to just be, if this top function is maybe y equals some f of x, and on the bottom we have some y equals g of x, then the height is going to be h of x equals the f of x minus the g of x, just the top minus the bottom. So all I'm doing right now is finding basically this dimension, the height of that little rectangle. And it's just going to be whatever the equation is of the top curve minus the equation of the bottom curve will give me the height difference that I'm looking for. So here's my h of x, here's my dx. I've accounted now for this part is this part, this part is this part. We're summing them all up. I've accounted for the 2 pi. So what about this r of x? Well, the r of x is the radius from whatever axis we're rotating around. And in this case, the radius is the distance from here out to that rectangle. So there's my r, the distance from the axis of rotation out to where the rectangle is. And notice, all that r is just whatever the x coordinate is of where this rectangle is occurring. So even though this looks like an r of x, we can really replace this with just x. So let's go back to green as a default color here. So this r right here is the same as this x right here. When we spin this thing around, the radius from the axis of rotation out to the point that we're interested in for that particular shell is just whatever the x coordinate is, assuming that we're rotating around the y-axis. If we were rotating around a different vertical axis, if I made the axis be over here at like -1, I would have to take the difference between the x coordinate of interest and x equals -1. And we'd wind up doing x minus a -1, and we'd wind up with x plus 1 for this radius if the axis were instead over here that we were rotating around, if that makes some sense. So here's our picture, and what it ultimately simplifies to is, and then we'll go over to the other equation, we ultimately get that the v is going to be equal to 2 pi, and this is the picture that goes with it, the integral from a to b of x times, in this case, our top function, f of x, minus our bottom function, g of x, dx. There is our integral for this particular picture. If I took a similar region over here, so let's do the example for the other case. In this case, here's my x and my y, and hypothetically those, maybe a and b are still the same 2 points. I'm going to try to draw roughly the same shape. So our shape is, oh, there we go. Close enough. So this shape here is meant to be the same as this shape here. Obviously not super accurate, but close enough. Okay, so in this case, looking at this same shape, still having this be y equals f of x on top, having y equals g of x on the bottom, and in fact, let's make it so it's smooth all the way on both of these. This will just make life a little simpler. And hopefully you'll see why in a minute. But if not, it's a good topic for us to discuss at some point and think about. Maybe I'll do a discussion post on this. So there's the shape. It's bounded on top, it's bounded on bottom. Here's going to be my C and D. And I want to rotate around this axis now. I want to rotate this shape around the x-axis. And if I want those cylindrical shells, that means I need to be taking horizontal slices. And so, if we do this exact same thing, what we'll wind up with is the following. So let's look and see how this is going to all work out. So now I'm rotating it around this axis. It's going to make a donut oriented kind of this way instead. And if I want to find that volume, I'm suggesting that this formula up here is what I'll need to do. So let's put in some of these different pieces. Well, first of all, the thickness of our little rectangle is our dy. There's our little thickness, so to speak. The radius, if you want to think about it this way, is now the distance from the x-axis up to the rectangle. So now this is the r. And if you think about it, all that really is whatever the y-coordinate is where this rectangle occurs, what height it occurs at. So in this case, I can replace the entire r of y with just a y. It's the height of our rectangle. And what we're calling the height over here, it's very confusing. So the radius is the thing that goes in the vertical direction. Maybe I'll stop using the word height to go with that. The radius is the y-coordinate. The y-coordinate in the vertical direction is the same as the radius, the distance from the axis of rotation. Hopefully that's more clear. Now the height that I'm referring to as h in our equation, that is this distance on the rectangle. So this distance here is what we're calling our h of y. And in this case, I need to know some different equations. I need to know the equation of this bound on this side. And so let's change it to what letters? I've already used F and G. I don't want to use H. Oh, come on. Let me just cheat, because we aren't actually going to care about this one. I'll erase this one. Pretend we don't have that one. Let's call this one over here y equals g of x. So we've got now two different things bounding it. This is our upper equation. This is our lower equation. But notice the way that they're written right now, it's y equals g of x, y equals f of x. They're functions of x. We need them to be functions of y. So I would have to solve this equation for x. We would have to solve this and find it as, I'll call it a capital F of y. And this one over here, same thing, we would have to solve it for x. X equals capital G of y. We would have to solve this equation for the other variables, so there's some extra work involved. And ultimately, our h of y would look like the following. It would just be this one minus this one, the f of y, capital F of y minus the capital G of y. That would be our h of y. So in this case, our volume is going to be the same thing. There's still going to be a 2 pi. Now we're integrating with respect to y. So I need to integrate from the lower bound in y up to the upper bound in y, from c to d of our radius. Let's come back and give us some room here. The radius, r of y, which we just said is just y. And then I need to multiply that by the height of this thing, which is dependent on whatever y coordinate we happen to be at. And that is going to be the f of y minus the g of y dy. So basically this part here, again, just to make things clear, this r is the same as the y coordinate. This r was the same as the x coordinate in the other drawing. And that is this piece. The dy, that's this little tiny thickness. And our h of y is right here. It's just the difference between this one and this one. The difference between what we're calling, in a sense, the top or the right side and the bottom, the left side of this rectangle. So that's sort of the picture we're looking at. And that's where these formulas come from in the book. So we can do the same type of integral, but in this case using using a cylindrical shell. Okay, so I want to do one example of these, but I just want to point out this all has to do with the way that we orient our rectangles, the way that we slice up our region compared to relative to which axis we're rotating around. So when we rotate around the y-axis and slice vertically, we're going to get these shells. If I was rotating around the y-axis and slicing horizontally, we would wind up with the washer method that we had before. And similarly over here, if I slice horizontally and rotate around the x, we get the cylindrical shell. But if I were to slice this thing vertically and rotate around the x-axis, we would wind up with the washers, just like we had in the previous section. So hopefully this makes some sense. As we do some problems and practice this more and more, you'll start to get a sense of when you should do which approach. And I'll talk about some of the pros and cons and try to give you some guidance on how you can decide which method is going to be the easiest. And we can look at that after we've knocked some examples all the way out of the way, maybe in another video. Okay, so let's do an actual example of this. Let me not do it in blue. So let's do an example sort of beginning to end of one of these types of problems. I want to find the volume of the solid formed by rotating the region bounded by, let's see, I want to do y equals x to the fourth plus 2x squared plus 1, y equals 1, x equals 1. Let me see, let me put in the word and x equals 1 about, so we're going to rotate this region about x equals 2. So just looking at this problem is terrifying. And if you don't draw the picture, it's going to remain really difficult. So draw the picture. Draw the picture. This might be a little bit scary. If you want to use a graphing utility, that's probably okay here. But ultimately, this is just a choric. It looks like a slightly squished, flattened parabola. We know it's going to be shifted up 1. And we can get a sense of what this looks like. So go ahead and graph it if you want on a graphing utility. I'm going to draw it for us. Oops. Right here. So here are my x and y axes. Let's draw the easy boundaries first. So y equals 1. That's going to be, let's call this a height of 1 right here. So I'm going to slice horizontally. We're also slicing at x equals 1. So here's 1 and 1. I'm going to slice vertically right here. I want to rotate around x equals 2, which is this line right here. So this is what we're rotating around. And lastly, the quartic is going to go through this point right here and then come up. And I should draw this line a little better. Hopefully I'll get better at using this tablet as the semester goes on. And it intersects up here. We can try to figure out this point of intersection. I'm going to draw it, but hopefully we'll see that in just a minute. So where would this point intersect? All we need to know to kind of figure out where it's going to intersect is to plug in x equals 1 into this thing. And I think I just, yep, I drew it 1 too high. I miscounted my dots. I want it to intersect right there. So if I plug in x equals 1, which is the equation of this line, if I plug x equals 1 into this equation, I'll get 1 to the 4th, which is 1, plus 2 times 1 squared, which is 2, plus another 1. So 1 plus 2 plus 1 gets me up to an ultimate height of 4. And so this is the region that I'm interested in. And we are rotating it around the vertical line x equals 2. And when we do that, we're going to get a shape that looks like the following. It kind of looks like a volcano, basically. So it's going to look like this. Actually, I guess we can see that edge. These edges in here are going to be dotted. We ultimately can't see this interior part, so let me dot them. Okay, hopefully that makes some sense when you see it drawn that way. That is the shape that we are trying to find the volume of. That's the shape we would get if we rotated this red region around this line. It would look something like this. And we are trying to build, we're going to solve or find this volume using rectangular shells. So basically, or sorry, cylindrical shells. So these are going to be rectangles going this way that we then wrap around this thing to build our cylinders, and then successively wrap another one around that, another one around that, another one around that, and so on to build up this shape. So we're going to wrap around a bunch of these cylindrical shells to get our volume. Okay, so our volume is going to be 2 pi times the integral. Let's take a look at this and see if we can figure out which of these two forms up here is going to be relevant without having to go back and reference the pictures up there. To get these cylindrical shells, we are slicing our thing vertically. And that means for us, each little thickness is a delta x or y. It is a delta x. And so ultimately this whole equation that we're about to do is going to be done with respect to x. So for us, the bounds of the region that we care about, it looks like, based on our drawing, we have an intersection right here and right here and right here. We are going from 0 to 1. Those are the bounds of integration of our red region in the x direction. It ranges from a minimum of 0 up to a maximum of 1 based on the picture that we've drawn here. Okay, so there's that. Now we need our radius. So remember, the next piece we need is our radius. Here we just had x, but we had x because in this case we were rotating around the x-axis. Now we're rotating around this line, x equals 2. So if I want to figure out, say, this little rectangle, I need this distance here. That is going to be my radius, my r of x. And what is the distance? Well, if I'm looking at this particular rectangle that has a coordinate of x, how far is this distance of this rectangle at x to the axis of rotation, which is at 2? The distance is just 2 minus x. That plays the role of our radius. This is our r of x. It's the distance from the axis of rotation at 2 to the point of this particular rectangle that we're interested in, which occurs at point x. And if we did a different x value, that radius would increase. So if I was doing the rectangles over here towards the left, the radius would be almost 2 because the x coordinate would be close to 0, and we would get a value here very close to 2. If we are looking at rectangles towards the right end at x equals 1, the radius would be very close to 1 because x would be close to 1, and we'd have 2 minus 1 being 1. So this formula is the radius. It's the distance from the axis of rotation to the particular point of interest for whatever rectangle we happen to be looking at. So far we've got the 2 pi accounted for, we've got the bounds of integration, we've got our r of x. The last thing we need is what plays the role of our height. And that is just the difference in the top and bottom curves bounding our rectangle that we've got here. So the top curve is given by the chordic equation that kind of looks like a parabola, but smushed. And the bottom one is this horizontal line, which is y equals 1. So I'm going to multiply by its height, which is x to the 4th plus 2x squared plus 1, put that in parentheses, minus 1. Let me change that to a square one there. So this is the top. This plays the role of our f of x, and this plays the role of our g of x. And together they combine to give us our height, h of x. And lastly, we got to remember our little tiny thickness of our rectangle, which is our little tiny delta x or dx in this case. So there is what our integral actually looks like. We can carry this integration out. It looks scary, but really the scary part of this integral is algebra. So let's see if we can make something of this. So I'm going to get the 2 pi integral from 0 to 1, and I'm just going to work on cleaning this up. So the first thing I want to do is cancel this plus 1 with this minus 1. That'll make life a little bit easier. And then I just need to FOIL out the 2 minus x with whatever's left in here, which is just the x to the 4th plus 2x squared. So I'm going to FOIL these two terms together, and we will get 2x to the 4th. That's the 2 times the x to the 4th. Then I'll do the 2 times the 2x squared, and that'll give me plus 4x squared. Then I will do the negative x times the x to the 4th, and that'll give me minus x to the 5th. And then finally, I will do the negative x times the 2x squared, which will give me minus 2x cubed. And then I can't forget my dx. So there's what I get when I FOIL those out. This is just a big, ugly, long polynomial, but it's not hard to do. We'll integrate that, and we will get 2 pi times, when I integrate this first one, it's going to be 2/5 x to the 5th. The next one's going to be plus 4/3 x cubed. Again, I'm just using power rule, knowing that the power is going to go up by 1 to a factor of 5 in this, or a power of 5 in this case, which I didn't write. Good catch. So the power goes up by 1, but to make up for the factor we'd pick up if we took the derivative, we also need to divide by whatever that power is. If you guys just remember the power rule for integration, that's all I'm doing here. The next one's going to be minus 1/6 x to the 6th, and then minus 2/4 x to the 4th, which we can obviously simplify if we want. And we're evaluating this between 0 and 1. And luckily, all of these terms involve x, so when I plug in the lower bound of 0, I'm not going to get any contributions, so I really only need to worry about the number 1 at the high end. When I plug that in, I will get 2 pi times 2/5 plus 4/3 minus 1/6 minus 2/4, which simplifies to 1/2. So that's what it looks like. I've got to find my lowest common denominator. You can do this on a calculator if you want. It looks like it's going to be 30. So let me just do that real quickly here. 2 pi, might as well complete one of these, practice our mental arithmetic here. 2 pi, doing a base of 30, 2/5 is going to be 12 out of 30, plus 4/3 is going to be 40 over 30, minus a 1/6 is going to be minus 5 over 30, and then minus a 1/2 will be minus 15 over 30. And adding these two up, we get 52. From these, I'm going to subtract off 20 from that 52, and we will wind up with 32 over 30. So we've got 2 pi times 30, 32 over 30, which we can obviously simplify a bit. Let me cancel this with this, and we will call it 32 pi over 15 as our final answer. And luckily, yep, it matches my notes. Didn't screw it up, hopefully. So this is the idea, and this is basically the difficult end of what one of these problems could look like. So give this a shot, try those homeworks, and later on, we'll come back to this topic and we will discuss why should I use a cylindrical shell versus a washer. Maybe we'll look at a handful of examples, certainly in time to review for the first exam, which is still a ways off. But when we review for that exam, we'll discuss which method should you use when. Hopefully, as you do the homework, you'll start to kind of get a little bit of intuition for when one method's going to work better over another method. But I'll try to clue you into some of the reasoning behind why one method might be beneficial or easier relative to another.